start. So our second speaker today is Professor Jiming Ma from Fudan University, China. So his title is Menger curve in the sphere and the spherical CR uniformization of closed hyperbolic three orbifolds. So let's welcome. Please.
Okay, so thanks for the introduction, and I also would like to thank the organizers who invited me to speak here. So today I will talk about the Menger curve in the three sphere. So here, no, it is. I'm sorry. So, but if yeah, okay. I will talk about Menger curve in the three sphere, and the spherical CR uniformization of closed hyperbolic three orbifold. And this is a joint work with Baohua Xie from Hunan University. And so my talk today will have three parts. The first part is I will talk about something about the embedding of Menger curve in the three sphere. And the second part, I will talk something about uniformable spherical CR structures on three manifold. And in the third part, I will talk about a little on complex hyperbolic geometry and a little on the proof of our main result. Okay, so so first we recall the Menger curve. So we denoted by kappa, which is a one-dimensional connected, locally connected and measurable compact space without locally separating parts. And also it contains the topological image of any curve. Okay, just like the definition of the contour side. The standard Menger curve in the three space can be obtained as follows. By this I mean, so first we take a standard cube here, we denoted C0, and we subdivide it into 27 pieces, right? And into 27 subcubes. And let's see one, the union of the smaller subcubes which intersect the one skeleton of the C0. And then we repeat this process and on each subcube again and again to definition of Cn, and then the standard Menger curve is by definition the intersection of all of these objects. So it is just the limit. Okay. So here is a picture here. So we first have a standard cube here in the three space. And then we subdivide it into 27 sub piece, right? Like this guy. Sorry, here, right? And the C1 is just the piece here, C1 piece here, piece here, and piece here, piece here, piece here, piece here, and also this ones. In other words, so in other words, we neglect so the piece. In other words, we neglect the piece of this guy and this guy and this guy. So and we repeat this process into infinity. Then we get the so-called standard Menger curve here, standard Menger curve. Okay, so and then we say the standard Menger curve is annotated in the three space, right? We just call it is annotated, and here it is comparing to the case of knots in the three sphere or in the three space. Recall that here are two knots. The left one is a standard circle in the three sphere, so it is annotated, right? And the second one is a three-four, and which is a annotated knot in the three sphere. And so So notice and unnotedness of the Menger curve in a free space, or in a free space is well defined up to isotopy. So, for example, embedding of Menger curve in the free space is annotated if it is isotopic to the standard one, then it is called annotated. Otherwise, then it is called annotated Menger curve, right? So just like the case of noted node and unnoted node, right? Okay. So in some sense, so today we do not consider S1 embedded in S3, but we consider Menger curve. Right, Menger curve embedded in the free sphere, right? Okay. Here is a noted Menger curve. So you can imagine this one is noted since the fundamental group of the complement of it is not the free group, right? Okay. So here, right now we have a Gromov hyperbolic space, and the boundary X is the Gromov boundary. I will not give the precise definition since it is not important today. And then some of the examples, if you have a free group of at least 2 generators, then the boundary of the group, if we consider the calligraph of it, then the calligraph of the group is a metric space. Then so we can say whether it is a Gromov hyperbolic space. Then we can consider it's a Gromov boundary. Then for the case of a free group, then the boundary of it is the contour side. And in other case, for example, for the case of a surface group, G is at least 2, right? So it is a hyperbolic surface group. Then the boundary of the surface group is a circle, so it is just the S1, right? And the little complete case is the compact hyperbolic manifold of dimension 2. Then the fundamental group of the compact hyperbolic manifold is also hyperbolic. Then the boundary is just n-1 sphere. And here and also for the case of complex hyperbolic space of complex dimension n, right? So and then the boundary of it is also a Gromov hyperbolic space. Then the boundary of it is a 2n-1 dimensional sphere. So today we just consider n equal to 2, so we get S3, right? Okay. Today we just consider the case. So 2-dimensional complex hyperbolic space, and the boundary of it is S3. Okay. And also consider the group here. We have a group G63. So by 6 I mean, so the group here is generated by 6 generators: A0, A1, A2, A4, A3, A4, and A5. And so it has 6 generators. And 3 means every generator has order 3. And we have also 6 another relations. I mean, so AI and AI plus 1 are cumulative, right? So for each of I. So this is an abstract group. So then it can be solved. G is a Gromov is a hyperbolic group. Then with boundary the Menger curve, right? It is given by Bogin. And with also we do not need to calculate this guy. So the group here, G63, is the group we are interested in today. So for example, if we consider G62, right? And then it is given by somehow like this guy, A0, A5, and also AI square is ID. And then AI plus 1 is also equal to AI plus 1 AI. Then it is just the Cauchy group. And it is waterly surface group. So, but that's the case. But that's from 2 here, from out the 2 out of 3. Then it is then the boundary of it is Menger curve. So it is more complicated. So for today, we just consider 2-dimensional complex hyperbolic space. So we have Hn2, right? And then the boundary of it is 3 sphere. And we also consider a group here, G63, which has a presentation like this Y, and we just consider the group and the space. Okay, for today. Okay. And Granier in 2015 constructed a discrete convex cocompact and feasible representation though of the group here to the Lie group here, and the Lie group PU21 is just the holomorphic isometric group of the 2-dimensional complex hyperbolic space. So then the limit site of the presentation is just homomorphic to the boundary of the group here, and this is just the Menger curve, right? Menger curve. Okay. Then so we have a Menger curve, and embedding in S3. Right? So in other words, from a very special representation of the group here to the Lie group here, then we have an embedding of the Menger curve into the 3 sphere. Then we want to know so what we can say about the embedding, right? Okay, this is what we will study. Okay, very interesting. Okay, so so it is conducted by Misha Kapovich 2 years ago. So and the Menger curve limit site about here. This is just here. It's isotopic to the standard Menger curve, right? In the 3 space or in the 3 sphere. So yeah, in other words, so Misha Kapovich conjectured the Menger curve limit site above is annotated in the 3 sphere. Okay. And the second part of the conjecture is that furthermore, the constant 3 manifold, and also in fact it should be 3 orbifold. Okay, it's a hyperbolic 3 manifold. So by here hyperbolic, I mean so 3 hyperbolic structure of dimension 3. Okay, so omega here it's that's the complement of the limit side. So from omega here to the 3 manifold, rho G63. Then this is orbifold curving. Orbifold curving map. Okay, but of course, so it is an infinite curving, and the omega here, the fundamental group of omega here is very complicated. So and what we study is here. It's the 3 manifold here. Okay. Okay. So and so the result it's this one. The 3 orbifold here, but the infinity of the representation, though 6G3 is closed hyperbolic 3 orbifold O, and then with the so since it is a 3 orbifold, then it has an underlying space. The underlying space is a 3 sphere, and also it has some singularity locus. So the singularity locus is a chain link here, C6 minus 2, and the chain link here is J/3 code. Okay, so in other words, so we have answered the second part of Misha Kapovich conjecture. Okay, and to also to our knowledge, so the three orbifold over here, that's the stream. It's the second one. It's the second explicit example of closed three orbifold, which would means uniformable spherical shell structures after the first examples given by Richard Schwartz, so nearly 20 years ago. Okay. So here is the chain link C6 minus 2. Here C6 means six components, right? 6 components. So this is 1, 2, 3, 4, 5, 6, right? And here minus 2 means here is a twist here. Minus 2, right? And also since it is J over 3 code, so here it should be J over 3, and is J over 3 single lattice, J over 3. Okay. So in other words, so we have solved the three orbifold at the infinity of the representation rho G3 6 3 here, three manifold give us three orbifold like this one. And this is the first step, and the second step is to solve the orbifold here is hyperbolic. Okay. This is our result. Okay. And one of the technical result here is that let D be the so-called discrete domain of the group here on the two-dimensional complex hyperbolic space. With a well-chosen center, we can ignore it then. So we can solve the intersection of the discrete domain, and omega is just the vector set, which is the complement of the limit set. So then the intersection omega is a solid torus in the three sphere. So here the boundary of it is just a three sphere. So the outside is that D and the intersection of D and omega. And from the picture, it is easy to solve. It is easy to see it is solid torus, but it needed to prove seriously. Okay, so and our result by this I mean, so the first one is hyperbolic of the three orbifold, and the second one is the solid total here seems to be strong evidence of the first part of Misha Kapovich conjecture, but right now we cannot prove Kapovich conjecture. Okay. So this is just the first part of my talk, and the second part of my talk is about uniformizable spherical structure, shell structure on three manifold. Okay. So so the relationship between topology of the manifold and the geometry of the meeting is a canonical topic. And for example, certain work on three manifold has also shown that geometry has played an important role to in the study of topology of three manifold. And a spherical shell structure here on a three manifold is a collections of charts, right, modeled on the boundary of the complex hyperbolic space, right, here, and then on the ordinate chains are restrictions of transformations from the Lie group here, right. So in other words, so a spherical shell structure is a GX structure. Here G is the Lie group here, and the X is the topological space three sphere. Okay. But in contrast to the result on other geometries on manifold, there are relatively few examples to know about the spherical structures on three manifold, and in particular, so it is very difficult in general to determine whether a three manifold admits a spherical shell structure or not. So, and today we will pay attention on a special kind of spherical shell structure. As I mean, so uniformitable spherical shell structure. So, what is the meaning of uniformitable? Right. So, if we have a group, if we have a discrete subgroup gamma acting on the Swiss field or acting on the complex hyperbolic space here, and then we have the regular set, right? Or maybe it is the set of discontinuity. Then we have a three manifold or three orbifold M here, which is just the omega gamma over gamma. So the modular action of gamma. So from omega gamma to gamma to omega gamma, right? This is the three manifold, and here it is a covering map, right? And in fact, it is orbifold covering map. So if a three manifold M here can be obtained in this way, so we first have a discrete subgroup and have omega gamma, and then we have the covering map. So we have constant space M here. If a three manifold can be obtained in this way, then we say the three manifold admits uniformitable spherical shell structures. Okay, so it is a special kind of spherical shell structure. So constructing discrete subgroup of the Lie group here can be used to construct some uniformitable spherical shell structure on three manifold. Okay, and so complex hyperbolic triangle groups provide rich examples of discrete subgroup of the Lie group here. For example, the study of deformations of complex hyperbolic triangle groups was began by Goldman and Park in 1992. So by complex hyperbolic ideal triangle groups, I mean, so we consider a group here. Here it is HC1, and this is also asymmetrical to HR2, right? And here, so it is cusp here infinity. So it has the so-called delta infinity triangle infinity triangle group here. So complex hyperbolic triangle group is a representation of formula group here. It is generated by three order two element, right? Into PO21, then it is called a complex hyperbolic triangle group, right? And Goldman and Park provide a proper subinterval of the modular space of complex hyperbolic triangle groups, infinity, right? Since by this I mean the modular space of delta infinity to this one it's an interval. Okay, it's an interval. Okay, and the this part is a function case. So it is discrete and faithful. But any part here we need to solve whether it is discrete or faithful. Okay, and Goldman and Park put like a proper subinterval of the modular space of the presentation of the complex hyperbolic triangle group into PO21 gives discrete and faithful representations. Okay, and moreover, they formulate the conjecture on the necessary and the sufficient condition for the representation into this group is discrete and faithful. And several years later, So Richard Schwartz proved Goldman-Parks conjecture in 2001. Okay, and so we now give some explicit example of Cuthbert hyperbolic manifold with admitting uniformable spherical CR structures. So recall that by uniformable we have this group here, and with embedding in PO21. Right? So the first one is given by Richard Schwartz in 2001. And in fact, she just consider the deformation of the complex hyperbolic ideal triangle group, and got a report that the group is degenerating. Then we saw the three manifold at the infinity is commutable to the Whitehead link complement. In other words, so the Whitehead link complement admits spherical uniformable spherical CR structures. And in 2017, so John Parker and Will gave another uniformable spherical CR structures on Whitehead link complement. These two structures are not the same. So, okay. And the second explicit example is given on the figurative knot. So I think everyone should know the figurative knot, right? And it is given by the Hall and Fabel in 2015. Right? And then, so in 2019, so August showed some feelings on the Whitehead link complement also admits uniformable spherical CR structures. And so myself and Baohua Xie, so the two three manifold. So M038 and S090 is just in the snappy list, right? Snappy list. So these are two Cuthbert hyperbolic three manifold. And we saw this two manifold also admits uniformable spherical CR structures. And moreover, so and we also saw the so-called magic link, and also admits spherical CR structures. Okay. The one of the goal of our paper, I believe our paper is the first step to show then feelings of the magic link should contains all of the uniformable spherical CR structure above. So it means the dead feeling of the last one should contains all of the examples above. Right? This is one of the motivations of our paper here. So and the example here, all of here are just cut. So cut. And so we consider here the closed case, right? So explicit closed hyperbolic three manifold or three orbifold, right? Orbifold. What it means, uniformable spherical CR structures. So the first one is also given by Richard Schwartz. So let W be a three orbifold with the underlying space in a three sphere, and whose singular locus is a two components links L, equipped with a J/2 co-structure. Okay. So here is a closure of closed sweep grid here. So the sweep grid is just given by this guy. So sigma 1 and sigma 2, right? So it is 15 times, right? Times. And here is sigma 1 and sigma 2 minus 2. So it is like this guy. So in 3 times. And just consider it's closer, right? Like this guy. Then we also have the G2 co-structure, right? G2. In fact, it just has two components. Then Richard Schwartz showed this hyperbolic 3-orbifold, closed hyperbolic 3-orbifold also admits uniformable spherical Xie structures. And this is in fact the first example of closed hyperbolic 3-manifold uniformable spherical Xie structures. And the second explicit one is the 3-orbifold we given today, right? We given today, which is C6 maybe -2 and the G2 code, G3 code. Right. Okay, this is just the second explicit example. So I think that this is the second part of my talk, and on spherical uniformable spherical Xie structures. Okay, and in the third part, I will talk about a little on complex hyperbolic geometry and on the proof. Okay, so here, if we consider the vector space C21, this is just the vector space C3, and but equipped with the embedded form right here, and this has a signature 2, 1. So here 2 means plus, right? And the signature, the other value here is plus, and 1 is minus. So the metric here has 2 positive added values and 1 negative added values, right? So then so let's just give the embedded form. Then the embedded form divides the vector space here into 3 parts, right? And which is V minus, V0, and V plus. So V minus is just the set of parts such that the embedded form on it is negative. And similarly, we have V minus, V0, and V plus. Okay. And we also has a canonical projection from the vector space, but without the 0 vector into the complex projective space CP2, right? Then the complex hyperbolic plane, so it is just the 2-dimensional complex hyperbolic space. It's just the image of V minus in the complex projective space. Okay, that's the image of it on map P here. Okay, and its boundary, a boundary of infinity is the image of V0 in CP2. So we denote it by boundary of the HCP of C2. Okay, and if we take some standard lift of G1, G2, but the third coordinate is 1 of a part here in 2-dimensional complex hyperbolic space, then it is negative only if it satisfies this inequality. So in other words, so it's C2. It is just a four-ball light, topologically, right? And the boundary of HC2, right? It's just the boundary of the four-ball, so it is a 3 sphere. Okay. This is the space we are integrating today. And so we have the matrix, the Bergman matrix, which is the matrix complex hyperbolics are integrating. So the matrix here is that. So we consider the formula here. So here it is real, right? And positive. Output is 0, right? So the Bergman matrix is just given by the formula here, right? And this definition is independent of the choice of some of lift of the right in HC2. or maybe we will say just in C3. Right. Okay. This is the metric we are used, right? And the complex hyperbolic plane HC2, right? The Kähler manifold of constant holomorphic sectional curvature -1. So we denote by U21, the Lie group, which is the amide form preserving complex linear transformations, and the PU21 is the group modular scalar matrix. So we just consider a modular three matrix omega times I, and also omega squared times I. So omega is the root of 1, right? And the group of holomorphic isometric of the complex hyperbolic space here, two-dimensional one, is just the Lie group here, PU21. And it is sometimes convenient to work with this group, which is a threefold carving of this guard. So the full isometric group of the complex hyperbolic space is just from this guard by adding just one element. So alpha, where alpha here is given on the level of homogeneous coordinate by complex conjugate here. Each element of it is take its conjugate. So now we consider total geodesic submanifold of complex hyperbolic space. And in fact, there are only two kinds of total geodesic submanifold of 3-dimension in two-dimensional complex hyperbolic space. The first one we call the complexless or complex geodesics, which are represented by somehow like this guy. So HC1, which is a subspace of HC2. Okay. So one-dimensional complex hyperbolic space is a subspace of two-dimensional complex hyperbolic space, right? Which has a codimension 2. And the second one is the so-called Lagrangian planes in HC2, which is just the case of the two-dimensional hyperbolic space is a total geodesic subspace of two-dimensional complex hyperbolic space, which also has a codimension 2. So, and since the remaining sectional curvature of the complex hyperbolic space is non-constant, there are no totally geodesic hyperplanes. So there are no total geodesic codimension 1 subspace of complex hyperbolic space, which is different from the case of three-dimensional hyperbolic space. So, and so we consider a complex line, which is just HC1, just the embedding in HC2, right? Which is just a compacted line, and we have a so-called polar of it, a polar of L is just the unique vector, which is perpendicular to this complex line with respect to the amide form. So which is just similar to the case of real hyperbolic space, which is L here, which is just HC1, and here it is HC2, and here it is polar vector denoted by maybe by n here. So for nx here, xn is 0, right? Is 0. Okay. So n the polar n is the so-called polar. Okay. And so in other words, so any part here, which is just in maybe so the projector of V class, right? And any C line here, there's a one-to-one correspondence. Okay. So so from any complex line, which is just HC1, right? And totally embedding the HC2. And also with the polar vector C, so then the complex reflection of auto n here fixed in the complex line, right, is given by the formula here, right? So today we just consider n equal to 3. Okay. Yes. Today we just consider the case of n equal to 3. And even though we call it a reflection, but in fact it is a rotation. Rotation in HC2. And it is a rotation along two-dimensional space. It is HC1 in HC2. So topologically, it is a rotation. Okay. So we have the definition of complex reflection of order n. Today we just consider the case of n equal to 3, and then we consider the representation of Granier. So here is the picture here. So we have HR2, right? This plane is just HR2, that's in the HC2. And we have right angled regular hexagon P, that's in this HR2. So here it is right angled here it is right angled. Right? And the regular right angled the regular rectangle hexagon P has 6 vertices, x0 and x1, x2, x3, x4, and x5. So any 2 points here determines convex line. With here it is HC1. And also the 2 points here also given HC1. And here also we have HC1. And here we have HC1. And also here we have also 6 HC1. So then we consider all the 3 complex reflection. Complex reflection above the 6 HC1, right? So here we have all the 3 complex reflection. We also have a complex reflection of all the 3 here, and we also have all the 3 complex reflection of the 3. And here, since the first the triangle here, it is rectangle, and in the case of HR2, so the HC1, the 2 HC1, maybe C1 and C2, right? Which just intersect in a port, maybe just in a port X1, and this is perpendicular. So this give the relation for the 2 out of the 3 complex reflection are commute, right? So in other words, from the picture here, from the regular rectangle hexagon in the hyperbolic space, which is embedded in 2-dimensional complex hyperbolic space, then we have 6 complex reflections, and the xi and the x and the alpha I and the x alpha I plus 1 are common. So then we have so with that gamma J in the complex reflection. Then so we define a map rho by rho A J B gamma J. So we call G63. This is by A1 and A5, that's generated by A1 and V5, and AI 3 times of ID, and also AI plus 1 equal to AI plus 1 AI, right? Okay, So we have a group, we have a presentation row from the group here, G63 to PO21. Okay. So and all for the generators here, all for the other three generators here are complex reflections now. Complex reflections. Okay. And this is the group representation we used here. And we just prove our result using the so-called discrete domain. And I think I should omit some of the definitions of discrete domain. And here, I just have some pictures. So, so I think this is one pixels in our paper. So why we should get the three manifold at the infinity of the orbifold O, right? And so from the picture here, we can write down explicitly the fundamental group of O, right? We can write down the fundamental group here for more discrete domain. We can write down the fundamental group of 8. Then from the fundamental group of the three manifold of the infinity, and then we consider another guy. This is isomorphic to the orbifold fundamental group of the three orbifold with underlying space, the three sphere, and singular with singular locus of which is they all three called chain link. So we have isometric to this guy. This step is not difficult, but to get the presentation here is a little difficult. Okay, and so at this step, so we get explicitly the three orbifold with the infinity. So we get three orbifold of the infinity of rho G 6 3 right. But now with the next step we don't show the three orbifold is hyperbolic. But to show it is hyperbolic, it is really hyperbolic. It's not difficult. And in fact, from two different feelings of the so-called perfect link. One component is with the coefficient of this guy, and the other one is the other components with this guy. So it is a hyperbolic three orbifold, right? Three orbifold. And we can also show. So the three orbifold here is a cover of our initial three orbifold. Then since this guy is hyperbolic, so this implies this guy is hyperbolic. Okay. Okay. Then from all of these steps, we can prove our main result. And recall that we proved is a three manifold with the infinity for a particular representation of a very special group G63 is a closed hyperbolic three orbifold, which is in fact the second explicit one is the second explicitly closed hyperbolic three manifold, which admits uniform spherical structures. Okay. So I think I should stop here. Thanks for your attention.
So let's thank Professor Jiming Ma. So any questions?
Yeah, I have a question and I would
Yeah.
like to ask. So You presented few examples which are very famous related to white link and to chain link,
Yeah.
and also some other recent examples. Do you understand the general situation? How many such examples? Are there some special families?
I think there are many. So there are many. Sorry. I think there are many hyperbolic free manifold with through the limits uniformable spherical structures, but any explicit examples it's difficult to prove. By difficult I mean, so right now the should use something with on photo domain or duty domain, and I mean so to prove it seriously it is difficult. The difficult part is just in complex hyperbolic geometry. The difficult part is not in free manifold, but in complex hyperbolic geometry. Right. Any example is difficult to obtain. So, for example, the case of the figure 8 knot, I think the proof given by the Hall and Fabel maybe 60 pages, I think, at least. And the example by Richard Schwartz and also has more than 50 pages. It is difficult to write down every detail.
And did you check is it corresponds to arithmeticity of the orbifold? For example, initial examples definitely are arithmetic. White link, figure 8 knot.
Pardon?
Do you know there is the idea of arithmetic groups and arithmetic?
Yes.
So the initial examples definitely are arithmetic. I mean, white link, figure 8 knot, and so on. What do you know about other examples? Are they arithmetic too?
So here by arithmetic, you mean so arithmetic in real hyperbolic geometry yes. So I think it is such the concordance, right? I think, and for the case of the so-called figure 8 which admits spherical uniform spherical shell structure, it is also arithmetic in the sense of complex hyperbolic geometry, right?
Oh, okay.
I think our example here, the example here today, I think it is not hyperbolic. I think it is not arithmetic in the sense of complex hyperbolic geometry, but I'm not sure. But I think it's not arithmetic.
Okay, thank you.
Thank you
very much.
Right.
Okay, so if no questions, let's thank Professor Jimmy again.
Okay.
So we will